So I'm creating this video as an intro to phase. I'm making this video because when I'm talking to folks about pro audio engineering, phase comes up a lot. And I think it's one of those things that seems more obscure than it really is. It seems like a really abstract concept, but really it's describing, I mean, it's so simple, I think that we just tend to overthink it. So I found a series of images that I think will help sort of wrap your head around what's really going on. And when you hear some of these terms, uh, it should hopefully make more sense. So here we show just that straight link here between a circle and a wave. And I'm sure you've heard of a sine wave. Sine is part of geometry, and it's related to a circle. I won't get into the geometry, but you can think of a wave as being a circle rotating. And so if the beginning is at 0 degrees, it's 0 amplitude. Then we have 90 degrees uh, at max amplitude. We have 180 degrees is at 0. 270 degrees is at negative max amplitude, and then it comes back to 0 again. It's right back where it started. Now, this degree doesn't really need to start anywhere. I think convention, it starts at 0, but you could start up here. And if you wanted to call this 0, and then you wanted to know the difference in phase from this point to this point, you know it's 90 degrees. Or from this point to this point is 90 degrees. As long as you go a quarter of a wavelength, wherever you start, wherever you end, is going to be 90 degrees. And same thing from 0 to 0. If we go from this point to this point, it's 180 degrees. If we go from this point to this point, it's 180 degrees. I'll shift to the next photo. Now here, it's just a simpler illustration, but it's showing two waves, two identical waves that happen to be separated. Now this, depending, right here it says time, but this could also be distance as well. So there's two different ways that this is often represented graphically, and here it's time, but it's equally could be distance, and it would mean the same thing. We have two waves, when two identical frequency waves, and when this one's at its peak, this one's not at its peak. When this one's at its peak, this one's not at its peak. And the difference here, you can find the identical part of each wave, and then that would be the phase difference. And we can figure that out in terms of degrees, which would be unique to this particular wavelength. Different wavelength, this distance would probably be a different number of degrees. So in this next image, we have two waves, similar to the previous one, where you have two identical waves. One is shifted in either time or space. But what we're doing here is we're showing you what the combined output is when you add these together. So if there was two speakers and one of them was just slightly in front of the other, so this peak would hit your ear before that peak would hit your ear, the combined sound wave that reaches your ear will be this one. And it's a little bit hard to see, but you can tell that since there's a phase shift here, it's about 90 degrees phase shift, because where that is at its peak, if I come down, this is at its 0 point. So it's about 90 degrees. And so you can see they add together, and they do add together to make a slightly louder signal. But what I want to point out here is that look at the phase. So we show this one is its peak here, this one's its peak here, and the peak for the combined wave is in the middle of the two. And that's what happens. This is a form of phase distortion, because the phase that's reaching, that ends up being constructed at your ear, is neither the phase of the first one nor the second one. And then here's an animated version of that. So I like this because it keeps one of the waves stationary, so you can kind of see how the blue wave here, you can think of the blue wave being either shifted through time or space, and the combined wave is black, and it'll tell you when it's constructive and when it's destructive. And the really important thing to understand about this is you see how the black line, it's moving. Like you see this thing moving, even though one of the waves that is used to construct it isn't moving. And this is really important in audio engineering because if you have two sources, like let's say you have two speakers and they're near each other, but they have a different distance from the listener's ear, different frequencies will construct and destruct depending on the length of the frequency. And it'll anything in between. A lot of people think of like the problem is either fully destruct or fully construct. And when you're engineering things, like you're planning on where these two events happen, total construct and total destruct. But in between, you have this phase distortion. You don't just have amplitude distortion, you have phase distortion. This is what I was talking about before. So you can put two things together, and at one specific frequency, it might appear that you're not taking or adding any volume or a modest amount, but you will be, in many cases, altering the phase of the result that comes out of it. And you don't want to do that. Phase itself gives your brain some characteristic information. And it's not like you're thinking to yourself, oh, that I could tell that one frequency is like 90 degrees off from that other frequency. That's not what happens. But you can definitely tell, the human brain can tell that there is something different. You won't be able to say what it is, but you'll be able to know something's different. And here's an example of a whole bunch of different waves, a whole bunch of different frequencies. And let's just imagine that what we're looking at is a very characteristic noise, something like a human singing voice, which has many different layers of frequencies together. And what I'm going to do is I'm going to copy this and paste it on top, and I'm going to drag it across so that you'll be able to see as I drag this over. Oh, I didn't do that right. Copy. There we go. So now as I drag this over, look how there's a difference. The image behind is staying still. And let's see how far I drag it before one of these frequencies lines up again. So it's going to be the bottom one because it's the shortest frequency. So I'll move it the shortest distance before I come back again. So there it is. So these two signals are now lined up as far as the pink frequency is concerned, but the rest of the frequencies don't line up. And if we tried to add them up, what does that mean? That means that there is a phase shift. Well, let's keep going. Let's see if there is a time we can move this to where it would line up and it wouldn't be weird. Let's keep going. So we have, it looks like the blue one will line up first, but none of the others do. Go a little bit further, we get the pink one lining up again. Go a little bit further. Looks like the green one's gonna line up now. So the green one's lined up. None of the rest do. All right, let's keep going. Keep going, keep going, keep going. We get pink again, and we get orange lined up there. There's orange. It looks like red's gonna be next. Is red gonna be next? Yes, red. Let's see, red. And then almost blue. Let's see. Actually, red and blue, look, red and blue get really darn close. So that's the only spot we found so far where two frequencies have lined up in their phase, but none of the rest do. So let's keep going. So I got pink again. and pink again, and then it looks like we'll get blue. Oh no, that's green. And then I'll reach the end. So you get the idea. If you wanted to delay this sound and add it to itself again, there will be frequencies that end up combining. There'll be frequencies that don't combine. And then there'll be frequencies that get phase shifted. And it's all going to be different. And that's where phase distortion comes from. And it's a real big problem with sound systems because you have many, many different speakers handling different parts of the spectrum. And where they overlap, all of the frequencies have to arrive at your ear at the same time, or it's not going to sound right. You'll hear it, and if it's words or something, you'll understand it, but it will not sound as clear as it would if everything was in phase. And that's all for this video.